Let's take a look at our Turvy problems, 6 and 7. The Monticello High School swimming pool is an inverted cone with a height of 20 meters and a radius of 5 meters. It's being filled by Mr. Blunden with a hose which pumps water in at a rate of 3 cubic meters per minute. They're asking us when the water level is 2 meters, how fast is the water level rising? That's for problem 6. And then how fast is the radius changing at that moment? That's problem 7. So we're going to get 2 answers. They want us to express our answers in meters per minute. Okay, so first of all, let's draw this crazy looking pool. It's a cone-shaped pool. It seems like it's pretty deep if it's 20 meters high. So there's a cone, 20 meters this way. This is the container, remember? And there's a radius of 5 meters. So I'm going to label these values right on my picture because they are constant. The container itself is not changing. What is changing is the water inside. So Mr. Blunden, he's filling this bad boy up, and they're putting water in, right? So water is going in. What is it, a hose? So he's got the hose going and it's pouring water in that direction. And so the level of water is filling up. Okay, now the water also makes a cone, right? So the water has a radius, which is changing, and it has a height, which is changing as we fill this thing up. And we've talked about those concepts before. The measurement 3 cubic meters per minute, that tells us at what rate the volume is changing. So one thing that I haven't written on my picture yet, but I will just kind of label it right here, is there is a volume of water in this cone, and it is also growing. And when they tell us that the rate is 3 cubic meters per minute, they're telling us the rate, the derivative, at which the volume is changing. And so that means dV dt equals 3 meters cubed per minute. Okay, now for number 6 here, we are told that the water level is 2 meters at the time that we're interested in. So that means H equals 2, and we are asked to find the rate at which the water level is rising. So we're asked to find dH dt. And we need a formula that relates our 3 variables: our volume, our height, and our radius. Well, if you look back at your geometry cheat sheet or you remember to your geometry teacher's class, you'll remember that the volume of a cone is 1/3 pi r squared h. So that's good news. We have a formula, but the bad news is we've got some extra variables in there that we don't have information for. So before we proceed, I need to figure out how to deal with the radius of this water. The radius of the cone itself, the container, is 5. It's constant, but this radius down here is changing. And so I need to find a way to include that in my formula. Well, the good news is these are similar triangles. So did I write 10 on the side of my... You guys can't... you're not here to yell at me. But this 10 is wrong. Isn't this thing 20 meters high? Yeah, so I apologize for that. But you'll notice that the blue water is going to be similar to or proportional to the entire container. So if the height of the container is 20 when the radius is 5, that means that the radius is 1/4 of the height. So I can write a relationship between the radius and the height, and I can write R equals 1/4 h, or better known as h over 4. And what I'm going to do is I'm going to put that h over 4 in right here. If you can eliminate variables ahead of time, it usually makes your life easier. So I am putting down V equals 1/3 pi times h over 4 squared times h. I replaced r with h over 4. And now I'm just going to simplify this a little so I can do my power rule. This is 1/3 pi h cubed over 16. And let's simplify it a little more. My goodness. 16 times 3 is 48. So this is going to be 48 pi. Excuse me. It's going to be 1 over 48 pi h cubed. This is the formula that I want to take the derivative of implicitly. And then I'll plug my numbers in. So the derivative would be dv over dt for the v equals 3 over 48 pi h squared times dh dt. And to finish this problem off, what I need to do is plug in 3 right here, plug in 2 for h, and then solve for dh dt. And with a little bit of algebra, which I'm not going to show on the slide because I'm running out of room, I end up with dh over dt equals 12 over pi, and that is meters per minute. So that's the answer for problem 6. And I've run out of room, so I'll start problem 7 on the next slide. But you get the idea of how that's going to work. Now, for problem 7, just so you know, I don't need to redraw the picture or even redo the setup because they say they want to know the dr dt at that moment. So I'm going to work with this equation down here to find the relationship between dh dt, which I know is 12 over pi, and dr dt, which I currently don't know. But that's the only thing I need. I need to know that r equals h over 4, and I need to know that dh dt is 12 over pi. Remember that our h is 2 at this moment. So let me go to another screen and we'll wrap up number 7. So as I said from the last slide, we do have some important information. We know that dh dt is 12 over pi. We know there's a relationship between r and h. And so all I'm going to do is I'm going to do implicit differentiation on this equation, r equals h over 4, and then I'll be able to relate the rates and solve for dr dt. So when I do the derivative of r, that's just a 1 dr dt. The derivative of h over 4 is 1/4 times dh over dt. And then since I know dh dt is 12 over pi, to figure out dr dt at the moment in question, I just do 1/4 times 12 over pi. And if I'm not mistaken, that is 3 over pi. And so my rate for the radius, dr dt, is just 3 over pi meters per minute. And we're done. Now, the key to this problem and what made this one more challenging, and this happens a lot with cylinders and cones, is that the container itself helps us discover the relationship between measurements in terms of the stuff that's in the container. So for us, the cone and the relationship between the 20-meter height and the 5-meter radius helped us determine the relationship between the radius of the water and the height of the water that's inside the cone. Once we figured out that the radius was 1/4 of the height, we were able to complete the rest of this problem. First, it helped us get rid of variables in the original equation, and then down here at the end, it helped us figure that rate for the radius. Sorry about that. By exploiting that relationship and then taking the derivative. So that's a tough problem. Lots of good calculus going on there, and really a lot of algebra and relationships too. So hopefully this helped. And I'll be working on a few other problems too and submitting those videos as I get them done. Let me know if you need anything else. Take care.